TSMC's front-end innovations. The semiconductor industry stands at the precipice of a profound historical transition. For more than half a century, the relentless drumbeat of technological progress has been dictated by Moore's Law, the famous observation that the number of transistors on a microchip doubles roughly every 2 years. This continuous miniaturization has democratized computing, transforming room-sized mainframes into the sleek smartphones in our pockets and enabling the massive data centers that power modern artificial intelligence. However, as we approach the latter half of the 2020s, the physical dimensions of these microscopic switches have shrunk so dramatically that measuring them in nanometers, billionths of a meter, is no longer sufficient. The industry is now crossing the threshold into the Angstrom era, where critical chip dimensions are measured in tenths of a nanometer, a scale where the individual atoms comprising the materials begin to dictate the physical behavior of the device. At the absolute forefront of this transition is Taiwan's Semiconductor Manufacturing Company, the world's largest and most advanced dedicated independent semiconductor foundry. As the primary manufacturer for global technology titans ranging from Apple and advanced micro devices to Qualcomm and NVIDIA, Taiwan Semiconductor Manufacturing Company's technological roadmap effectively serves as the baseline for the future of global computing. Between the years 2025 and 2028, the foundry is executing a breathtakingly ambitious sequence of node transitions, specifically the N2, A16, and A14 process generations. This period represents the most dense concentration of simultaneous architectural, material, and lithographic revolutions in the history of the Silicon Age. To comprehend the magnitude of this transition, we must embark on a comprehensive exploration of front-end semiconductor fabrication, the demise of traditional transistor architectures, the radical restructuring of power delivery networks, the geopolitical and economic battles over extreme ultraviolet lithography, and the fundamental rewriting of the materials used to build our digital world. Decoding the Silicon Factory, the art of front-end fabrication. To truly appreciate the engineering marvels of the Angstrom era, one must first understand how a microchip is actually constructed. Semiconductor manufacturing is a tale of two distinct halves, the front-end process and the back-end process. The technological leaps defining the N2, A16, and A14 nodes are entirely contained within the front-end process, making it essential to define exactly what this stage entails for the general public. In the simplest terms, the front-end process is the stage of manufacturing where the actual microscopic electronic circuits are painstakingly built directly onto a perfectly flat, highly polished disk of ultra-pure silicon known as a wafer. Imagine the silicon wafer as an empty plot of land, and the front-end process as the construction of billions of microscopic skyscrapers, roads, and power lines on that land. This construction does not happen all at once. Rather, it is achieved through a repetitive cycle of highly controlled physical and chemical steps. The process begins with rigorous cleaning of the wafer, followed by oxidation, which creates a protective and electrically insulating layer of glass-like material on the silicon surface. Next comes photolithography, arguably the most critical step, where complex geometric patterns are optically projected onto the wafer using extreme ultraviolet light. This light alters a light-sensitive chemical coating called a photoresist, creating a microscopic stencil. Once the stencil is in place, the wafer undergoes etching, where harsh chemicals or high-energy plasmas physically carve away the exposed material, leaving behind the desired physical structures. This is followed by ion implantation, a process where the silicon is bombarded with specific elemental impurities, such as boron or phosphorus, to precisely alter its electrical conductivity, transforming it from a mere rock into a controllable semiconductor. Following this, various thin films of insulating dielectrics and highly conductive metals are deposited onto the wafer using chemical vapor deposition or physical sputtering. Because this process involves stacking dozens of layers on top of one another, the wafer must be repeatedly subjected to chemical-mechanical planarization, a sophisticated polishing technique that ensures the surface is absolutely perfectly flat before the next layer is applied. The front-end process is entirely dedicated to the creation of the active devices, the transistors that do the actual computing, and the dense network of microscopic metal wiring that connects them together. This process requires absolute perfection, taking place in clean rooms that are thousands of times cleaner than a hospital operating theater, as a single speck of dust can destroy thousands of microscopic circuits. It is only after the front-end process is entirely complete and the wafer is populated with hundreds of identical, fully formed integrated circuits that it is handed over to the back-end process. The back-end involves dicing the wafer into individual chips and packaging them into the protective plastic or ceramic housings that we eventually see in our computers and phones. While modern back-end packaging has become incredibly sophisticated, the fundamental processing power, energy efficiency, and logic density of a computer chip are intrinsically and permanently defined by the atomic-scale architectures forged during the front-end process. The physics of miniaturization and the limits of FinFET. To understand the front-end roadmap of Taiwan Semiconductor Manufacturing Company, we must first understand the fundamental building block of all digital electronics, a transistor. A transistor is essentially an electrical switch. It consists of three primary components: a source where electrons enter, a drain where electrons exit, and a gate that sits between them. When voltage is applied to the gate, it creates an electric field that allows current to flow through a channel from the source to the drain, representing a digital 1. When the voltage is removed, the flow stops, representing a digital 0. The faster and more efficiently this switch can turn on and off, the better the microchip performs. For the past decade, the industry has relied on a specific transistor design known as the FinFET. In older planar transistors, the channel connecting the source and the drain was completely flat, and the gate sat on top of it. However, as transistors shrunk to incredibly small sizes, the flat gate lost its ability to properly control the flow of electrons. Electrons began to leak across the channel even when the switch was supposed to be turned off, a phenomenon driven by quantum tunneling and short channel effects. This massive leakage generated massive amounts of unwanted heat and drained battery life. To solve this, engineers created the FinFET, which took the flat silicon channel and turned it on its side, creating a three-dimensional raised fin. The gate material was then draped over this fin, surrounding it on three sides. This three-sided control allowed the gate to firmly clamp down on electron leakage, saving power and allowing miniaturization to continue down to the 5 nanometer and 3 nanometer generations. However, as the industry pushes toward the 2 nanometer threshold, physics has once again caught up with human ingenuity. At these impossibly small dimensions, even wrapping the gate around three sides of the fin is no longer sufficient to stop electron leakage. The channel has become simply too short, and the electrostatic control of the FinFET architecture has reached its breaking point. If chip makers were to continue shrinking FinFETs, the resulting chips would run incredibly hot, consume vast amounts of electricity, and fail to deliver meaningful performance improvements. A radical new architectural paradigm was required to save Moore's Law. The N2 node and the gate-all-around nanosheet revolution. The solution to the limitations of the FinFET is the defining characteristic of Taiwan Semiconductor Manufacturing Company's N2 process node, which is slated to enter high-volume mass production in the final quarter of 2025. This node marks the foundry's historic transition to the gate-all-around field effect transistor, specifically using a stacked nanosheet architecture. The N2 node represents the most significant architectural overhaul in transistor design in over a decade, and its successful implementation is paramount to the continuation of global technological progress. Imagine taking the vertical silicon fin of a FinFET, rotating it 90 degrees, and slicing it horizontally into several distinct ultra-thin ribbons of silicon. These silicon ribbons, or nanosheets, are suspended in the air, stacked perfectly parallel on top of one another, with tiny gaps between them. During the extraordinarily complex front-end manufacturing process, the gate material is deposited in such a way that it flows into these tiny gaps, completely encapsulating every single silicon ribbon on every 4 sides. Because the gate now surrounds the electron channel a full 360 degrees, the transistor achieves absolutely unprecedented electrostatic control over the flow of current. This total encapsulation yields tremendous physical benefits. First and foremost, it effectively eradicates the sub-threshold electron leakage that plagued the final generations of FinFETs. Because the gate has such a tight grip on the channel, the transistor can be turned on and off using significantly less voltage. This reduction in operating voltage is the holy grail of semiconductor engineering, as power consumption drops exponentially when voltage is reduced. Furthermore, the nanosheet architecture introduces a new dimension of flexibility for chip designers. In the FinFET era, designers were strictly limited by the discrete, standardized heights of the silicon fins. In the gate-all-around nanosheet era, the width of the silicon ribbons can be dynamically adjusted by the designer. If a specific part of a processor needs to perform heavy, high-speed mathematical calculations, the designer can use wider nanosheets to allow more drive current to flow. Conversely, if a section of the chip is dedicated to low-power background tasks, the designer can deploy very narrow nanosheets to strictly conserve battery life and save physical space on the silicon wafer. The resulting performance, power, and area improvements of the N2 nanosheet architecture over the previous generation are staggering. When compared to the highly refined N3E FinFET baseline, the N2 process delivers a substantial 10 to 15% improvement in processing speed when operating at the exact same power envelope. Alternatively, if a designer chooses to keep the processing speed identical to the previous generation, the N2 node can deliver a massive 25 to 30% reduction in total power consumption. This power efficiency is particularly pronounced at lower supply voltages. For instance, when operating at a highly constrained 0.5 volts, the N2 nanosheet transistors can boost clock speeds by 20% while simultaneously cutting standby power consumption by an astounding 75% compared to older designs. Alongside these remarkable speed and power enhancements, the transition to nanosheets enables a significant leap in miniaturization. The N2 process provides an approximate 1.15 times increase in overall transistor density compared to the N3E node. This means that chip designers can pack 15% more logic gates, analog circuits, and static random access memory into the exact same physical footprint. This density improvement is further augmented by innovations in the middle-of-line wiring, such as the introduction of barrier-free tungsten metal wiring. This advanced tungsten wiring reduces the electrical resistance at the point where the gate connects to the broader circuit by 55%, allowing the transistors to cycle faster and pushing the overall frequency of the processor higher. Bridging design and manufacturing, the power of DTCO and NanoFlex. While the sheer physical ingenuity of the gate-all-around nanosheet is remarkable, the physical scaling of transistors alone is no longer enough to guarantee generational improvements in a finished commercial microchip. In the modern semiconductor industry, the company that designs the chip, such as Apple designing the processor for the iPhone, is entirely separate from the company that physically manufactures it. Historically, the foundry would develop a physical process, hand a rigid set of design rules to the customer, and the customer would do their best to build a chip within those constraints. However, as the cost and complexity of manufacturing have skyrocketed, this disconnected approach has become deeply inefficient. To ensure that the immense potential of the N2 node is fully realized, Taiwan Semiconductor Manufacturing Company relies heavily on a deeply collaborative engineering philosophy known as Design Technology Co-optimization. Design Technology Co-optimization is the practice of developing the physical manufacturing process and the logical architectural design of the chip simultaneously, right from the very beginning. Instead of treating the physical silicon and the digital design as two separate realms, engineers optimize them together to find the perfect balance of performance, power efficiency, transistor density, and manufacturing cost. For the N2 generation, Taiwan Semiconductor Manufacturing Company has formalized this co-optimization approach through a proprietary suite of technologies branded as NanoFlex. To understand NanoFlex, one must understand the concept of a standard cell. When companies design complex processors containing billions of transistors, they do not draw every single transistor by hand. Instead, they use pre-designed building blocks called standard cells, which contain a small arrangement of transistors wired together to perform a basic logical function, much like a specific piece in a Lego set. NanoFlex capitalizes on the variable channel width capabilities of the new Nanosheet transistors to provide fabless designers with an incredibly versatile standard cell architecture. Specifically, NanoFlex allows designers to seamlessly mix and match standard cells of different physical heights within the exact same logic block of a chip. A designer can utilize short cells, which are physically highly compressed and optimized for extreme power efficiency and maximum area savings for the vast majority of the processor's background logic. Then, right next to them, the designer can place tall cells, which utilize wider nanosheets and are optimized for maximum drive current and raw performance for the critical pathways of the processor that handle intense calculations. This NanoFlex technology also incorporates a highly sophisticated 6-level voltage threshold system. By making subtle atomic scale changes to the materials inside the gate, the foundry can offer designers 6 different options for the exact voltage required to trigger the switch. This granular control allows designers to fine-tune the minimum operational voltage of their chips, achieving reductions of 20 to 35 millivolts compared to equivalent FinFET designs. As a direct result of this intense co-optimization, critical components like static random access memory cells on the N2 process can achieve a record-breaking density of approximately 38 megabits per square millimeter, capable of stable, reliable operation at astonishingly low voltages. By deeply intertwining the design tools with the manufacturing physics, NanoFlex empowers fabless customers to extract every single ounce of value from the highly expensive N2 silicon. The wiring bottleneck and the physics of power delivery. As the industry moves beyond the N2 generation, it faces an entirely different yet equally existential physical crisis. For decades, the primary focus of Moore's law has been shrinking the transistor itself. However, as billions of transistors are packed ever closer together, the microscopic metal wires required to connect them must also shrink. This dense network of wiring is known as the back end of line, and it is currently the source of a massive bottleneck that threatens to choke the performance of modern microchips. To visualize the problem, imagine looking at a cross-section of a traditional semiconductor. The microscopic transistors sit at the very bottom, buried in the silicon wafer. Above them towers a staggeringly complex three-dimensional metropolis of metal wiring, often stacked up to 20 layers high. In all traditional chip designs, this metal metropolis must serve 2 distinct purposes simultaneously. It must route the data signals between the transistors, and it must deliver electrical power from the outside world down to the transistors. As logic density increases, these data wires and power wires are forced to compete for the same incredibly limited physical footprint. To fit them all in, the copper wires are made narrower and narrower. This creates a severe physical problem. As a wire becomes thinner, its electrical resistance increases dramatically. For the data signal wires, this high resistance causes delays, meaning the transistors must wait longer for information to arrive, slowing down the entire computer. But for the power delivery wires, the problem is far more destructive. When electrical current travels down a highly resistant microscopic copper wire through 20 layers of complex routing to reach a transistor, a phenomenon known as IR drop occurs. IR drop is a fundamental principle of physics where the voltage of the electricity sags as it pushes through resistance. By the time the power navigates the tortuous maze of front-side wiring and finally reaches the transistor at the bottom, the voltage has dropped significantly. This starves the transistor of the power it needs to switch at high speeds, completely negating the performance benefits of advanced architectures like nanosheets. Furthermore, pushing power through these highly resistant wires generates massive amounts of unwanted heat, further degrading performance and damaging the chip. The front-side power delivery network has become a catastrophic traffic jam, and the only solution is a total architectural redesign of the microchip itself. The A16 node and the super power rail revolution. To break this fundamental wiring bottleneck, the semiconductor industry is executing a structural revolution known as the backside power delivery network. Taiwan Semiconductor Manufacturing Company will commercially introduce its highly advanced, proprietary implementation of this concept, designated as the super power rail in the A16 process node. Scheduled for high-volume mass production in the second half of 2026, the A16 node represents a paradigm shift in how integrated circuits are spatially organized. The super power rail technology solves the traffic jam by entirely decoupling the power delivery infrastructure from the data signal routing. In the A16 architecture, the towering metal layers on the front side of the silicon wafer are dedicated exclusively to the complex signaling networks required for data transmission. The power delivery grid is physically removed from the front and relocated to the previously entirely unused back side of the silicon wafer. Moving the power to the back of the chip is an engineering challenge of the highest magnitude. The silicon wafer must be physically flipped over, and the bulk of the silicon substrate must be shaven down to microscopic thinness to expose the underside of the transistors. Then, a new, highly efficient network of thick, low-resistance power wires is constructed on the back. What distinguishes Taiwan Semiconductor Manufacturing Company's super power rail from competing early iterations of backside power is its incredibly sophisticated contact methodology. Other foundries rely on intermediate vertical metal pillars called through-silicon vias to bridge the gap between the backside power grid and the front-side transistors. However, these pillars are relatively large and consume valuable physical space that could otherwise be used for transistors. In contrast, the A16 super power rail features a novel direct contact scheme. Microscopic nanovias are engineered to connect the backside power network directly into the source and drain terminals of every single individual transistor. This direct backside contact scheme is immensely difficult to manufacture, requiring lithographic overlay tolerances of a mere 3 nanometers, meaning the alignment between the front and the back of the wafer must be perfect down to the width of a few dozen atoms. However, by achieving this direct contact, Taiwan Semiconductor Manufacturing preserves the ultimate gate density and layout footprint of the chip. The resulting performance leap for the A16 node is substantial, making it the premier process technology for power-hungry applications such as artificial intelligence accelerators and high-performance computing graphics processors. When compared to the highly optimized N2P baseline process, the introduction of the super power rail in the A16 node yields an impressive 8 to 10% speed improvement at the same positive power supply voltage. Alternatively, it can deliver a 15 to 20% reduction in power consumption when operating at the exact same frequency and complexity. Furthermore, because the front-side metal layers are now entirely liberated from bulky power wires, the data signal lines can be packed much closer together, facilitating an overall chip logic density increase of up to 10%. By embracing the extreme mechanical complexity of the direct contact backside power delivery network, the A16 node permanently shatters the interconnect resistance bottleneck. The 1.4 nanometer horizon, the A14 node, and NanoFlex Pro. Following the deployment of the N2 and A16 platforms, the foundry roadmap progresses to the highly anticipated A14 node, representing the true 1.4 nanometer class of silicon fabrication. Scheduled for high-volume mass production in 2028, the A14 node is not merely an iterative enhancement of previous technologies. It is engineered as a full node generational leap. This node will serve as the foundational bedrock for the consumer electronics and data center architectures that will define the end of the decade. The technological core of the A14 node is the implementation of second-generation gate-all-around nanosheets. By 2028, the foundry will have accumulated 3 years of mass production experience with the first-generation nanosheets introduced in N2. This manufacturing maturity will allow engineers to implement profound refinements in the atomic structure of the A14 channel. The second-generation nanosheets will feature improved channel electrostatics, allowing the silicon ribbons to be placed with even tighter physical pitches. These refinements will further suppress sub-threshold leakage and allow for significantly higher drive currents to push through the transistor when activated. The projected performance, power, and area metrics for the A14 node underscore its status as a massive generational leap forward. When measured against the industry-leading baseline of the N2 process, A14 is engineered to deliver up to 15% speed enhancement at identical power levels. Conversely, if designers prioritize energy efficiency, the A14 node can provide up to 30% reduction in power consumption when operating at the same speed as an N2 chip. Furthermore, the aggressive dimensional scaling of the second-generation nanosheets will facilitate an impressive logic density increase of more than 20% over the N2 generation, allowing chipmakers to push the total transistor counts of complex processors well past current physical limits. Interestingly, the foundational A14 node, slated for 2028, will not inherently feature the super power rail backside power delivery network that was introduced in the A16 node. This is a highly calculated strategic decision based on the diverse needs of the global technology market. While high-performance artificial intelligence chips desperately need the extreme power density management of the super power rail, many other applications, such as mobile smartphone processors, edge computing devices, and specialty Internet of Things chips, do not require such extreme power delivery. For these clients, the traditional front-side power delivery network is perfectly adequate, and forcing them to adopt the mechanically complex and expensive backside power routing would needlessly inflate the cost of their products. Therefore, the base A14 node offers the raw transistor performance of second-generation nanosheets with cost-effective front-side routing. However, for the data center clients who demand ultimate performance without compromise, an enhanced variant, tentatively designated as A14P, is expected to integrate the backside power delivery network around 2029. To harness the absolute maximum potential of these second-generation nanosheets, the A14 node will introduce a major evolution of the design technology co-optimization framework dubbed NanoFlex Pro. While specific, highly technical specifications regarding the internal mechanics of NanoFlex Pro remain closely guarded industry secrets, it represents a substantial advancement in standard cell architecture design. NanoFlex Pro is anticipated to offer even greater granularity in per-block transistor width optimization and standard cell height mixing than its predecessor. It will provide fabless engineers with a vastly expanded toolset to sculpt the power, performance, and area characteristics of their silicon with unprecedented precision. This evolution will be critically important for maximizing the efficiency of on-device artificial intelligence engines within mobile smartphones, where rigid thermal constraints and strict battery limitations dictate the absolute limits of computational power. Lithography conundrum: standard EUV versus high NA. As the physical dimensions of transistors shrink well below the wavelength of visible light, the semiconductor industry is increasingly defined by the capabilities of its photolithography equipment. Lithography is the mechanism by which the intricate circuit patterns are optically transferred onto the silicon wafer. To print features at the nanometer scale, the industry utilizes extreme ultraviolet lithography, a process that borders on science fiction. Extreme ultraviolet lithography systems operate in a vacuum, where highly synchronized lasers fire at microscopic droplets of molten tin falling through the air. The laser vaporizes the tin into a superheated plasma, which emits a flash of extreme ultraviolet light with a wavelength of a mere 13.5 nanometers. This incredibly short wavelength is essential for carving the impossibly intricate features required for modern microchips. Because extreme ultraviolet light is absorbed by all matter, including glass lenses and even the air itself, the light cannot be focused using traditional optics. Instead, it must be bounced through a series of incredibly precise multi-layered mirrors, some of the flattest surfaces ever created by humanity, to project the circuit pattern onto the wafer. Traditionally, the resolution limit of these extreme ultraviolet systems is dictated by a mathematical concept known as the numerical aperture. In optics, a higher numerical aperture allows the system to collect light from a wider angle, resulting in a sharper, higher resolution image projected onto the focal plane. The standard extreme ultraviolet lithography machines utilized across the global semiconductor industry today employ an optical system with a numerical aperture of 0.33. However, to achieve the sub-2 nanometer feature sizes required for the A16 and A14 nodes, standard 0.33 numerical aperture machines face severe physical limitations. The features are simply too small for the machine to print in a single flash of light. To overcome this, foundries must resort to highly complex workarounds known as multi-patterning. Techniques such as self-aligned double patterning or self-aligned quadruple patterning involve taking a single incredibly dense circuit design, breaking it apart, and placing it across multiple different photomasks. The silicon wafer must then be run through the lithography scanner several different times, painstakingly building up the final ultra-dense pattern through overlapping exposures. While multi-patterning is highly effective, it drastically increases the number of processing steps, vastly inflates the time a wafer spends on the manufacturing line, and introduces extreme risks of overlay errors, where subsequent mask layers fail to perfectly align with the underlying patterns by margins of mere atoms. To permanently solve the multi-patterning dilemma, the Dutch equipment manufacturer ASML, the only company in the world capable of building these machines, has developed the next generation of lithography tools known as high-NA EUV. These mammoth truck-sized machines, specifically the TwinScan EXE5000 series, feature a massive 0.55 numerical aperture optical system. This advanced optical system is capable of resolving 8-nanometer critical dimensions in a single exposure. In practical terms, this means semiconductor engineers can print features nearly twice as small as before without resorting to the arduous, time-consuming multi-patterning process, thereby drastically simplifying the manufacturing flow and potentially reducing cycle times. The art of multi-patterning and the stitching problem. Despite the clear technological advantages of high-NA EUV, the transition to these new machines carries severe economic and technical penalties, creating a profound strategic schism within the global semiconductor industry. The high-NA EUV tools are exorbitantly expensive, carrying a staggering price tag of between $350 and $400 million for a single machine. Furthermore, the optical physics of the high-NA system introduces a highly problematic phenomenon known as anamorphic imaging. Because of the extreme angles required by the larger mirrors, the demagnification of the photomask is asymmetric. The image is shrunk 8 times in the scan direction, but only 4 times in the slit direction. Consequently, the maximum physical area that a high-NA machine can expose on a silicon wafer in a single flash, known as the exposure field, is cut perfectly in half compared to standard extreme ultraviolet machines. To manufacture large, highly complex logic dies, such as the massive processors used in artificial intelligence data centers, manufacturers using high-NA EUV must digitally stitch 2 half-field exposures together with flawless atomic precision. This stitching process requires the implementation of complex exclusion zones and novel design methodologies that can negatively impact the maximum clock frequency and power dissipation of the final chip. This technological crossroads has forced the world's leading foundries to place massive divergent bets on the future of lithography. Intel has aggressively positioned itself as the vanguard of high-NA EUV, securing the very first available machines from ASML and betting its entire foundry turnaround strategy on deploying the 0.55 numerical aperture tools for its upcoming 14A node. In stark contrast, Taiwan Semiconductor Manufacturing Company has opted for a highly pragmatic, deeply cost-driven strategy, deliberately deferring the adoption of high-NA EUV for the foundational A14 node. Executive leadership at Taiwan Semiconductor Manufacturing Company has determined that despite the increased complexity, extending the life of their current fleet of 0.33 numerical aperture tools through advanced multi-patterning remains significantly more cost-efficient than absorbing the massive depreciation and operational costs of the $400 million high-NA machines. Extensive economic modeling supports this cautious approach. Research indicates that a single exposure on a high-NA tool costs roughly 2.5 times more than a single exposure on a standard tool. Therefore, high-NA lithography only becomes financially viable when the alternative requires 3 or more standard EUV multi-patterning masks. By meticulously optimizing their physical chip designs and minimizing the number of overall mask increases, Taiwan Semiconductor Manufacturing Company can achieve the density of the A14 node using traditional extreme ultraviolet tools. This vital strategic decision ensures that the A14 node remains economically accessible for a broad base of consumer electronics clients, avoiding a massive spike in manufacturing costs. The foundry is confident in its ability to manage the complexities of multi-patterning, pushing the inevitable industry-wide adoption of high-NA EUV further down the roadmap, likely reserving it for the A14P variant or the subsequent 1-nanometer class nodes expected closer to 2030. Rewriting the Interconnect periodic table, the fall of copper. As the physical architecture of the transistor and the mechanisms of photolithography undergo radical transformations, the Angstrom era also mandates a complete reimagining of the fundamental elements on the periodic table used in semiconductor manufacturing. For nearly 3 decades, copper has reigned supreme as the undisputed conductive material of choice for the intricate wiring networks that route data through the back end of line of a microchip. The introduction of copper damascene technology in the late 1990s was a revolutionary breakthrough that enabled decades of continuous scaling. However, as interconnect lines approach a microscopic pitch of roughly 24 nanometers in advanced nodes, the physical properties of copper begin to break down dramatically. The failure of copper at the atomic scale is driven by 2 primary physical phenomena. First, copper requires the presence of diffusion barrier and liner materials. If pure copper is deposited directly into the insulating dielectric material of a microchip, the copper atoms will rapidly diffuse into the insulator, causing catastrophic electrical short circuits. To prevent this, the trenches carved into the silicon must first be lined with a microscopic layer of barrier metal, typically tantalum or tantalum nitride. At older, larger manufacturing nodes, this ultra-thin barrier layer was negligible. But as the copper wires scale down to widths measured in handfuls of atoms, the protective barrier layers consume an unmanageable proportion of the cross-sectional area, severely reducing the actual volume of conductive copper inside the wire. More critically, as the copper wire narrows toward the physical mean free path of an electron, severe quantum phenomena occur. Electrons traveling down the wire begin to violently collide with the microscopic surfaces of the wire and bounce off the internal grain boundaries of the copper crystalline structure. This relentless electron surface scattering and grain boundary scattering causes the electrical resistance of the copper wire to skyrocket exponentially. High resistance in the interconnect network cripples the speed at which electrical signals can propagate across the chip, causing severe resistance-capacitance delays. These delays are so profound that they can entirely negate the immense switching speed gains achieved by the advanced nanosheet transistors sitting below them. Furthermore, the intense current density required to push signals through these highly resistant microscopic copper wires generates immense electromigration forces. Electromigration is a destructive physical process where the flow of electrons acts like a rushing river, physically tearing copper atoms from their lattice and sweeping them away, creating microscopic voids that eventually sever the wire and cause catastrophic permanent chip failures. To address the impending physical death of copper interconnects, front-end materials engineering is aggressively transitioning toward alternative elemental metals, specifically ruthenium and cobalt, for the smallest, lowest-level interconnect vias and routing lines in nodes like A14. Ruthenium and cobalt possess vastly superior resistance to electromigration due to their higher physical melting points and higher activation energies compared to copper. This makes them significantly more durable under the extreme electrical stress of modern microchips. More importantly, at physical dimensions below a 40-nanometer pitch, the specific electron scattering properties of ruthenium and cobalt allow them to mathematically outperform copper in total line resistance. Ruthenium, in particular, is hailed as a miracle material for the Angstrom era. It has demonstrated the unique ability to be deposited without the thick, highly resistive barrier layers required by copper. By eliminating the barrier layer, a much greater volume of the microscopic trench can be filled with pure, highly conductive ruthenium metal. The adoption of ruthenium and cobalt binaries represents one of the most significant shifts in front-end material science since the 1990s, ensuring that critical data signals can travel rapidly between the 1.4 nanometer transistors without fatal resistance-capacitance degradation. Exploring the transistor channel of the future. While replacing copper solves the interconnect routing crisis, corporate research and development divisions are concurrently looking even further into the future, actively exploring radical new semiconductor materials to eventually replace silicon itself within the actual channel of the transistor gate. As physical dimensions continue to scale down relentlessly, the inherent mobility of electrons within a traditional bulk silicon lattice becomes a fundamental limiting factor. To enable continuous scaling beyond the A14 node toward future theoretical architectures like complementary field effect transistors, extensive research is being conducted on ultra-thin, two-dimensional transition metal dichalcoxides. A primary candidate leading this materials revolution is molybdenum disulfide. Researchers have successfully presented the first electrical demonstrations of two stacked nanosheet transistors utilizing a monolayer molybdenum disulfide channel. Unlike traditional silicon, which exists as a three-dimensional bulk crystal, two-dimensional transition metal dichalcoxides like molybdenum disulfide can be synthesized as atomistically thin sheets, literally a single molecule thick. These two-dimensional channels provide near-perfect electrostatic control for the transistor gate and completely prevent the chaotic electron scattering that plagues bulk silicon when it is carved down to atomic limits. However, integrating these exotic lab-grown materials into high-volume commercial manufacturing presents immense challenges. To overcome the difficulties of routing electricity into these ultra-thin materials, researchers have developed novel metallic contact methodologies, such as C-shaped wraparound contacts. These unique geometric structures drastically reduce the electrical contact resistance at the exact point where the metal interconnect meets the molybdenum disulfide, achieving exceptionally high drive currents and massive on-off ratios. Alongside two-dimensional transition metal dichalcoxides, intense research is also progressing on oxide semiconductor field effect transistors. These advanced transistors utilize novel materials like tungsten-doped indium oxide and tin oxide. Because these materials can be processed at much lower temperatures than traditional silicon, they hold the potential to be built directly into the metal wiring layers above the main chip, enabling true three-dimensional monolithic integration. Additionally, dense, aligned one-dimensional carbon nanotubes are being successfully integrated into experimental high-performance logic applications, displaying tremendous improvements in channel transductance and total gate control. While these highly advanced channel materials may not see high-volume manufacturing immediately in the base A14 node, they represent the aggressive, multi-billion-dollar material science pipeline required to sustain the Angstrom-era roadmap deep into the 2030s. The brutal economics of the Angstrom era. The transition to Angstrom-class silicon is not merely a triumph of quantum physics, optics, and materials engineering. It is an exercise in extreme, unprecedented economic investment. The financial burden required to construct the gargantuan fabrication facilities, purchase fleets of extreme ultraviolet lithography scanners, and execute the thousands of meticulous atomic-scale processing steps has pushed the fundamental cost of leading-edge silicon to historic, eye-watering heights. The Angstrom era is defined just as much by its brutal economic realities as it is by its technological breakthroughs. To understand the economics of the semiconductor industry, one must look at the price of a single processed silicon wafer. Historically, as transistors shrank, the cost per transistor plummeted, driving the tech boom. However, that trend has severely flattened. The sophisticated multi-patterning extreme ultraviolet steps, the implementation of complex barrier materials, the staggering power consumption of the tools, and the soaring costs of raw materials and ultra-pure cleanroom infrastructure have driven the price of a single 12-inch processed N2 wafer to an estimated $30,000. As the roadmap progresses to the 1.4 nanometer A14 generation, the economic forecast becomes even more imposing. To facilitate high-volume A14 production, massive capital expenditures are required. Taiwan Semiconductor Manufacturing Company is reportedly preparing an estimated $49 billion investment to construct 4 dedicated ultra-advanced fabrication facilities, collectively dubbed Fab 25, in the central Taiwan Science Park. To recoup these astronomical capital expenditures, industry analysts project that the cost of an A14 silicon wafer will surge by an additional 50%, reaching an astonishing $45,000 per wafer upon its commercial introduction in 2028. At a price point of $45,000 for a single disk of silicon, the financial barrier to entry for utilizing the world's most advanced front-end silicon process becomes insurmountable for all but the most heavily capitalized technology titans. This effectively restricts early adoption of the A14 node to premium smartphone architects, massive artificial intelligence data center providers, and dominant graphic processing unit designers who can absorb the costs and pass them on to consumers. The science of yield, defect density, and learning curves. Because the cost of the raw wafer is so astronomically high, the ultimate determinant of economic viability for both the foundry and the fabless customer is the manufacturing yield curve. Yield is the percentage of perfectly functional sellable microchips that are successfully harvested from a single processed silicon wafer. If a $30,000 wafer yields hundreds of perfect chips, the economics work. If microscopic dust, lithographic misalignment, or material impurities ruin half the chips on the wafer, the financial losses are catastrophic. Despite the radical, incredibly risky architectural shift from the proven FinFET to the completely novel gate-all-around Nanosheet, Taiwan Semiconductor Manufacturing Company's N2 process node has demonstrated an incredibly robust and aggressive yield learning trajectory. Official defect density metrics for the N2 process have been disclosed to be actively lower than those of the highly successful N3, N5, and N7 nodes when compared at equivalent stages of pre-production development. As the technology nears volume production, the N2 baseline yield hovers securely around 65%, with confident projections indicating a climb to 75% as the technology matures through its final mass production phase. This remarkably steep defect reduction curve is not an accident, it is the direct result of the foundry business model. Because Taiwan Semiconductor Manufacturing Company manufactures chips for dozens of different companies, it runs massive production volumes and a wide variety of different product architectures through its fabrication lines. This sheer volume of data acts as a massive feedback loop, accelerating the identification and remediation of microscopic fabrication flaws and optimizing the defect learning cycles far faster than competitors. By comparison, competitor yields at the emergent 2-nanometer node remain highly fragmented and uncertain. Intel's competing 18A process is reportedly hovering near 55% yield, while Samsung's equivalent gate-all-around SF2 process is struggling near a 40% yield due to persistent manufacturing bottlenecks in their transition to nanosheets. The staggering $45,000 projected cost of an A14 wafer illuminates exactly why design technology co-optimization frameworks such as NanoFlex and NanoFlex Pro are so absolutely critical to the modern semiconductor industry. When fabless semiconductor companies are paying tens of thousands of dollars for a single disk of silicon, any wasted microscopic space equates to massive financial hemorrhaging. Design technology co-optimization serves as the ultimate financial shield for these fabless customers. By working symbiotically with the foundry's physical rules from day one of the design phase, fabless engineers can meticulously curate their standard cell heights, tightly packing logic gates into the absolute smallest possible square millimeter. The ability to dynamically trade off power, performance, and area on a granular, block-by-block level using NanoFlex ensures that customers are extracting the absolute maximum computational output for every dollar spent on the highly expensive raw silicon. Without the intense spatial optimization provided by technologies like NanoFlex Pro and the immense physical area-saving advantages provided by the Super Power Rail backside delivery network, the economic viability of the Angstrom era would simply collapse under the immense weight of its own manufacturing complexity. The evolution of front-end semiconductor fabrication from 2025 through 2028 represents one of the most intense, concentrated periods of multidisciplinary engineering in the history of human technological achievement. The transition through the N2, A16, and A14 nodes is not a simple linear progression. It is a highly calculated, multi-front war against the terminal physical limits of the universe that have threatened to halt Moore's law. The replacement of the traditional FinFET with the gate-all-around stacked nanosheet in the N2 node secures the total electrostatic control required to continue scaling operating voltages down, saving immense amounts of power and preventing thermal failure. The introduction of the Super Power Rail in the A16 generation brilliantly untangles the catastrophic front-side routing crisis, relocating the entire power delivery network to the backside of the silicon wafer to eradicate debilitating IR voltage drop and dramatically accelerate high-performance compute architectures. Furthermore, the highly pragmatic, financially grounded decision to extend the life of standard 0.33 numerical aperture extreme ultraviolet lithography through advanced multi-patterning for the A14 node, while rivals absorb the astronomical, unproven costs of high NA EUV, highlights an acute awareness of the fragile economics governing the modern foundry business. Supported by a renaissance in atomic-level material science that is aggressively pushing ruthenium, cobalt, and two-dimensional transition metal dichalcogenides into the core lattice of the microchip, the front-end roadmap is technologically secured for the remainder of the decade. Ultimately, the success of the Angstrom era will be defined not merely by the mastery of quantum-scale electrons or exotic optics, but by the relentless pursuit of deeply integrated design technology co-optimization, ensuring that the staggering human and financial investments are justified by the unprecedented artificial intelligence and computational capabilities seamlessly embedded within the silicon. The global semiconductor industry is currently navigating one of the most profound technological transitions in its history, shifting its fundamental philosophy to accommodate the staggering computational demands of the modern era. For over half a century, the relentless drumbeat of progress was dictated by Moore's law and the science of front-end manufacturing. In the public consciousness, making a computer chip simply meant shrinking microscopic transistors and cramming more of them onto a single piece of silicon. However, as the physical dimensions of these transistors approach the size of individual atoms, the traditional methods of simply shrinking circuits have encountered insurmountable walls of physics and economics. The cost of designing and fabricating massive monolithic silicon chips has skyrocketed, while the performance gains from miniaturization alone have begun to plateau. In response to this existential threat to computing progress, the spotlight has rapidly and decisively shifted away from the front-end creation of transistors and toward the back-end process of packaging them together. This transition from monolithic silicon scaling to advanced three-dimensional system-level integration is the singular catalyst enabling the artificial intelligence revolution. At the absolute forefront of this movement is the Taiwan Semiconductor Manufacturing Company, which has architected a comprehensive advanced packaging ecosystem known as 3D Fabric. Through a meticulously engineered suite of technologies, the industry is systematically dismantling the bandwidth, energy, and thermal barriers that threaten to halt the advancement of high-performance computing. The invisible foundation, understanding the semiconductor back-end process. To fully comprehend the sheer magnitude and complexity of recent packaging innovations, it is necessary to establish a clear foundational understanding of the semiconductor manufacturing life cycle, which is universally divided into two distinct phases: the front-end process and the back-end process. The front-end process is the highly publicized, deeply complex phase where billions of microscopic transistors are etched, doped, and formed under raw circular silicon wafers using cutting-edge lithography and chemical deposition techniques. This stage requires a profound mastery of quantum physics, materials science, and extreme ultraviolet photonics. It is akin to constructing the complex internal architecture, the foundational structures, and the intricate electrical grids of a massive microscopic city. However, once the front-end circuit formation is complete, the silicon wafers are entirely non-functional in their raw state. They cannot communicate with other hardware, they lack external power delivery mechanisms, and they are incredibly fragile, susceptible to destruction from a single speck of dust or a minor fluctuation in humidity. This is precisely where the back-end process begins, fundamentally serving as the bridge between a fragile piece of silicon and a robust, consumer-ready electronic device. Historically viewed by many as a secondary, less glamorous phase of chip making, the back-end process is fundamentally responsible for taking that raw, fragile silicon and transforming it into a functional, protected, and integrated commercial product ready for the consumer market or the hyperscale data center. The traditional back-end sequence is a multi-step journey. First, the processed wafer is thinned down to reduce its physical profile, a delicate mechanical and chemical process that prepares the silicon for compact devices. Next, it is cut or diced into individual semiconductor chips, commonly referred to as dies. Once separated, these individual chips must be physically and electrically connected to a larger substrate or a printed circuit board, which serves as the translation layer between the microscopic connections of the chip and the macroscopic connections of the computer's motherboard. Following this delicate assembly, the back end encompasses the encapsulation of the chip in protective materials, hermetically sealing it to shield the delicate circuits from physical shock, moisture, and extreme temperature fluctuations. Finally, the packaged chip undergoes rigorous quality assurance and reliability testing to ensure stable long-term operation. For many decades, major semiconductor foundries focused almost all of their research and development capital on the front end, outsourcing the back-end assembly, packaging, and testing to third-party companies known as Outsourced Semiconductor Assembly and Test Providers, or OSATs. While the front end required bleeding-edge scientific breakthroughs, the back end relied heavily on mechanical engineering, thermal management, and precision soldering. Today, however, that dynamic has been completely upended. Because shrinking transistors has become exponentially more difficult, the burden of increasing computational performance has fallen directly onto the back end. Advanced packaging is no longer just about putting a plastic protective shell around a single chip. It is about taking dozens of different chips, often manufactured on entirely different front-end process nodes, and stitching them together so seamlessly that they operate as a single massive supercomputer. This convergence of front-end precision and back-end integration is the absolute cornerstone of modern artificial intelligence hardware, turning what used to be a basic protective enclosure into a highly sophisticated communication network that defines the speed of the entire system. The era of 3D fabric, a new philosophy in system-level design. Recognizing that the future of computing could no longer rely solely on shrinking transistors on a single piece of silicon, the Taiwan Semiconductor Manufacturing Company introduced the 3D Fabric platform. This ecosystem represents a comprehensive family of three-dimensional silicon stacking and advanced packaging technologies, designed specifically to unleash innovation for modern computing workloads. These workloads, which encompass cloud computing infrastructure, massive artificial intelligence neural network training, big data analytics, and autonomous driving, require a holistic, system-level optimization approach that traditional chip manufacturing simply cannot provide. The fundamental philosophy driving the 3D Fabric ecosystem is modularity, often referred to as the chiplet approach. Instead of attempting to manufacture an impossibly large monolithic silicon die, which is highly prone to microscopic manufacturing defects that can ruin the entire chip, designers can now build highly complex products by assembling specialized subcomponents. By splitting a massive logic processor into smaller, highly specialized functional blocks, or chiplets, companies can drastically improve their manufacturing yields. If one small chiplet has a defect, only that small piece is discarded, rather than an entire massive processor. Furthermore, this modularity allows chip designers to mix and match technologies. They can utilize the most expensive, cutting-edge front-end nodes exclusively for the core logic processors that require extreme computational power, while utilizing older, cheaper, and more mature manufacturing nodes for components like analog sensors or input-output controllers. This drastically reduces overall costs and shortens the time to market, as designers can simply reuse proven, reliable technology blocks from previous generations without having to redesign an entire monolithic architecture from scratch. The 3D Fabric portfolio is a vast umbrella that is generally categorized into back-end packaging technologies such as the chip-on-wafer on substrate and integrated fan-out families, and front-end three-dimensional stacking technologies such as system-on-integrated chips. However, mastering the physical creation of these packaging techniques is only one half of the equation. Connecting billions of transistors across multiple disparate chiplets introduces staggering complexities in thermal management, power delivery, electrical signaling, and structural integrity. A designer cannot simply glue two chips together and expect them to work. They require a deeply integrated supply chain and an entirely new software design ecosystem to simulate the physical realities of the final product. To navigate this unprecedented complexity, the Foundry launched the 3D Fabric Alliance as a monumental extension of its open innovation platform. This alliance is the first of its kind in the semiconductor industry, purposely built to accelerate the adoption, innovation, and production readiness of multi-chip systems. The alliance categorizes global partners into critical foundational pillars, including electronic design automation software providers, intellectual property developers, memory manufacturers, substrate suppliers, testing specialists, and outsourced semiconductor assembly and test firms. By collaborating intimately during the earliest research and development phases, the alliance ensures that everything from the physical machinery on the factory floor to the digital software design tools on an engineer's computer are perfectly aligned. A crowning achievement of this software-hardware co-optimization is the introduction of the 3D Blocks Open Standard, which has now evolved into its highly sophisticated 2.0 iteration. In the past, designing a three-dimensional chip was an incredibly fragmented and error-prone nightmare because different software tools created by different companies could not communicate effectively with one another. For example, the software used for thermal heat analysis could not seamlessly share its data with the software used for physical layout and wiring. To solve this catastrophic bottleneck, the 3D Blocks standard was created to serve as a universal, uniform hardware description language for advanced packaging, which is currently being adopted by the Institute of Electrical and Electronics Engineers as an official open standard. It models both the key physical stacking geometry and the logical connectivity of highly complex systems in a single, standardized, generic format across various abstraction levels, ranging from a basic black box representation to detailed graphical data system layouts. This standardization allows global electronic design automation partners to build highly interoperable software tools that speak the exact same language, making the integration of data from multiple third parties transparent and efficient. Furthermore, recent and ongoing evolutions of the 3D blocks standard incorporate advanced artificial intelligence-powered resource optimization. By leveraging machine learning and generative artificial intelligence, these tools can automatically explore the physical design space, managing the incredibly delicate interplay and multi-physics convergence between thermal coupling, power delivery networks, and electromigration across dozens of stacked silicon layers. This artificial intelligence-driven design automation significantly increases productivity, allowing engineers to transition from a conceptual chiplet architecture to a fully verified, tape-out-ready design in a fraction of the time previously required, effectively utilizing artificial intelligence to design the very hardware that will run future artificial intelligence applications. The anatomy of CoWoS, scaling the engine of the artificial intelligence era. If the 3D fabric ecosystem and the 3D blocks standard provide the software blueprints for the future of computing, the chip-on-wafer on substrate technology family is the heavy industrial machinery physically constructing it. The history of this platform dates back to its original development in 2011, serving as the foundational origin point for modern 2.5-dimensional integration. Over the subsequent years, it slowly evolved, achieving major production milestones in 2016 with early deep learning accelerators and continuously growing to support the most complex high-performance computing systems on the planet. Today, it serves as the foundational, non-negotiable packaging technology for the world's most powerful and sought-after artificial intelligence accelerators, including the flagship processors that dictate the pace of global machine learning research. The core unifying premise of the entire CoWoS technology family is the heterogeneous integration of highly complex logic processors alongside massive, towering stacks of high-bandwidth memory, all mounted together onto a single intermediary communication layer known as an interposer, which is then mounted onto a broader package substrate. As large language models and generative artificial intelligence networks have exploded in parameter size, the computational demands placed on memory bandwidth and logic density have skyrocketed to levels previously thought impossible. Processors are starving for data, and they need memory to be as physically close as possible with as many wiring connections as physically possible. This insatiable demand has forced the CoWoS packaging architecture to rapidly evolve into three distinct, highly specialized technological branches: the silicon-based CoWoS-S, the organic-based CoWoS-R, and the localized bridge CoWoS-L. The legacy, most mature, and most widely recognized variant is CoWoS-S. The S stands for silicon. This architecture utilizes a massive, passive silicon interposer as the foundational bridge connecting the logic chips to the high-bandwidth memory. Because the interposer is manufactured out of pure silicon, utilizing the same highly precise manufacturing techniques as the chips themselves, it allows for incredibly dense, microscopic, fine-pitch wiring. This results in extreme data bandwidth and impeccable signal integrity, ensuring that thousands of gigabytes of data can flow between the memory and the processor every second without degradation. To deliver power and move signals from the top of the package down to the motherboard, CoWoS-S utilizes deep trench capacitors and through-silicon vias, which are microscopic vertical tunnels drilled directly through the silicon. However, despite its unrivaled performance, CoWoS-S is fundamentally constrained by a harsh physical manufacturing boundary known as the reticle limit. The advanced lithography machines that print circuits onto silicon using light can only expose a certain maximum rectangular area at a single time, known as a reticle. Current CoWoS packages are pushing the absolute physical boundaries of manufacturing by stitching multiple exposures together, spanning up to 3.3 times the standard reticle size. Creating pristine, flawless silicon interposers of this immense macroscopic size is exceptionally difficult, highly expensive, and incredibly prone to yield issues. If a massive silicon interposer cracks or has a single microscopic wiring flaw, the entire package, along with the highly expensive processors and memory attached to it, must be discarded. To directly address the spiraling costs, yield constraints, and flexibility limits of pure silicon, the second variant, CoWoS-R, was developed. The R stands for redistribution layer. This technology completely abandons the expensive, fragile, full silicon interposer in favor of an organic interposer built utilizing advanced polymers and fine-pitch copper wiring. This is essentially a highly advanced derivative of the integrated fan-out technology originally developed for mobile smartphones, now scaled up for high-performance computing. The organic nature of this substrate provides a crucial game-changing mechanical advantage. It acts as a dynamic stress buffer. In massive, high-powered artificial intelligence chip packages, the logic dies, the memory stacks, and the substrates all heat up rapidly during intense computational workloads. Because they are made of different materials, they expand and contract at completely different rates, a phenomenon known as the coefficient of thermal expansion mismatch. In rigid silicon interposers, this thermal mismatch can lead to severe mechanical warping, cracked solder joints, and catastrophic reliability failures over time. The innate flexibility of the CoWoS-R organic polymer substrate absorbs this thermal mechanical stress, acting like a shock absorber. This significantly improves manufacturing yields and long-term durability. While CoWoS-R does sacrifice the absolute highest ultra-dense interconnect pitches of its silicon sibling, it perfectly balances cost, configurability, and reliability, making it the ideal packaging choice for large-scale networking switches, routers, and slightly less memory-intensive high-performance computing clusters. The ultimate future of massive-scale artificial intelligence computation, however, lies in the third and newest variant, CoWoS-L. The L stands for Local Silicon Interconnect. Designed specifically to shatter the reticle limits that bind CoWoS-S while maintaining its extreme performance, the CoWoS-L architecture is a masterful best-of-both-worlds hybrid. It utilizes an expansive, cost-effective organic substrate to provide broad signal routing and power delivery across the massive package. However, it embeds microscopic active silicon bridges, the local silicon interconnect, directly into the organic material, precisely and only where ultra-dense wiring is required. These tiny silicon bridges are placed strategically to bridge the microscopic gaps between the main logic processors and the high-bandwidth memory stacks. By stitching together these localized, tiny silicon segments within a much larger, forgiving organic structure, CoWoS-L completely circumvents the reticle limit. It can scale to unprecedented massive physical sizes, currently projected to reach interposer areas exceeding an astonishing 3,000 square millimeters. At this gargantuan scale, a single CoWoS-L package provides the sheer physical real estate and thermal headroom required for next-generation trillion-parameter artificial intelligence training models, all while maintaining the ultra-dense interconnectivity that was previously only possible with a traditional monolithic silicon interposer. The evolutionary roadmap for this technology is staggering. By the year 2027, the foundry plans to bring a massive 9.5 reticle-size CoWoS package to volume production, which will be physically large enough to integrate an unprecedented 12 or more independent stacks of next-generation high-bandwidth memory alongside leading-edge logic processors. This massive scaling is not merely a technical evolution, it is a strategic triumph that will dictate the architectural ceiling of the artificial intelligence infrastructure for years to come. The Great Capacity Race, Supply Chain Dynamics, and the 100,000 WPM goal. The sudden, meteoric, and largely unforeseen rise of generative artificial intelligence applications triggered a massive global surge in demand for high-performance processors. This overnight boom caught the global semiconductor supply chain entirely off guard. The limiting factor in delivering artificial intelligence servers to hyperscale cloud providers was not the front-end fabrication of the logic chips themselves. The bottleneck was entirely constrained within the advanced packaging phase. The highly specialized capacity required to manufacture these complex CoWoS packages simply did not exist at the immense scale required by the market. Consequently, an aggressive, unprecedented, and highly capitalized capacity expansion is currently underway across the global semiconductor landscape. Historically, the monthly output for these ultra-advanced packages sat comfortably around the 65,000 to 75,000 wafer mark. However, as customers drastically increase their wafer starts and press for tighter timelines, the industry is racing to virtually quadruple its advanced packaging footprint in record time. Current projections and aggressive expansion roadmaps indicate that CoWoS capacity will surge to over 100,000 wafers per month by the end of 2026, with some financial estimates projecting an eventual run rate of 130,000 wafers monthly. Achieving this massive industrial-scale ramp-up requires a vast, highly synchronized, and rapidly accelerating equipment supply chain. Because the back-end advanced packaging process has fundamentally lower entry barriers compared to the extreme ultraviolet lithography used in front-end manufacturing, which is dominated by a few massive European, American, and Japanese monopolies, a robust, localized supply chain of highly specialized equipment manufacturers is rapidly emerging in Taiwan to meet this insatiable demand. The expansion of these advanced packaging facilities relies on vast, heavy, precision machinery. To build a CoWoS package, a facility requires hundreds of highly advanced electroplating machines to deposit copper wiring, ultra-precise die bonders to place the chips, chemical molding machines for encapsulation, specialized thinning machines to grind down the silicon, automated ball placement machines for the solder bumps, stealth dicing machines to separate the dies, and specialized curing ovens to bake the organic polymers. Local Taiwanese equipment suppliers, leveraging decades of foundational expertise in heavy machine tools and mechanical processing, are stepping up to fill these massive equipment orders, experiencing monumental growth in sales as they localize the manufacturing pipeline. Specialized European suppliers are also contributing cutting-edge placement technology, such as the Datacon 8800 series bonders, which offer unprecedented 4-micrometer placement accuracy at high production volumes, critical for handling the delicate components of advanced artificial intelligence packages. Due to the severe time constraints imposed by the artificial intelligence boom, the traditional timeline for expanding a semiconductor facility has been completely upended. Where facility ramp-ups used to be planned meticulously in a step-by-step manner over several years, timelines from research and design finalization to peak mass capacity are now being compressed from 7 quarters down to a mere 3 quarters, demanding almost immediate operational readiness. Because of this blistering pace, localized procurement of this heavy packaging machinery is viewed as an absolute strategic imperative. Relying on overseas equipment shipments introduces unacceptable delays. Therefore, nurturing and utilizing a trustworthy local supply chain ensures the continuous, uninterrupted scale-up of artificial intelligence infrastructure while making massive orders with equipment makers during the earliest research phases. This expansion is occurring physically across multiple massive new facilities. A significant portion of the immediate new capacity is being brought online by retrofitting existing spaces, such as taking over old liquid crystal panel plants like the Innolux AP8 facility in the southern Taiwan Science Park to rapidly convert them into advanced packaging hubs. Furthermore, entirely new mega facilities are being constructed from the ground up, including massive planned expansions in Chiayi, which will eventually house 8 separate plants dedicated to system-on-integrated chips and futuristic panel-level packaging, alongside international expansions like the new advanced packaging facilities being constructed near the main fabrication plants in Arizona, scheduled to begin mass production as early as 2028. However, even with this aggressive internal capacity expansion, the sheer volume of orders from global chip developers is pushing the primary foundry to its absolute limits. To alleviate internal pressure and maintain focus on the most complex, high-margin CoWoS-L and CoWoS-S assemblies, the foundry has begun strategically outsourcing certain lower-complexity packaging tasks, such as basic redistribution layer manufacturing and simpler interposer preparations, to its major outsourced semiconductor assembly and test partners. Industry leaders like Advanced Semiconductor Engineering and Silicon-Ware Precision Industries are aggressively building out their own new production lines tailored explicitly to match the exact equipment, strict processes, and exacting quality standards of the primary foundry, with capacity expected to triple to tens of thousands of wafers monthly by late next year. This unprecedented collaboration is creating a broader, more resilient ecosystem across the entire advanced packaging sector, ensuring that multiple avenues of production are available to satisfy the unyielding global demand. Going vertical, system-on-integrated chips, and the magic of hybrid bonding. While the CoWoS family dominates the realm of 2.5-dimensional lateral integration, placing chips side by side on a flat interposer, true architectural breakthroughs require expanding computing directly upward into the third dimension. This is the exclusive domain of the system-on-integrated chip technology, universally regarded as the premier front-end 3-dimensional stacking platform. As the physical 2-dimensional footprint of chips becomes a severe limiting factor in densely packed data center server racks, vertical stacking allows for extraordinary exponential increases in transistor density. By effectively stacking a logic processor directly on top of another logic processor, or stacking massive amounts of high-speed memory directly on top of a logic core, designers can drastically reduce the physical distance data must travel, thereby virtually eliminating latency and power consumption. Historically, 3-dimensional chip stacking relied entirely on microbumps, tiny microscopic spheres of tin and lead solder that were melted in an oven to form electrical connections between two stacked silicon dies. However, as the industry pushes for higher and higher performance, solder bumps present severe, unavoidable physical limitations. First, they are relatively large, which places a hard physical limit on how many connections can be squeezed into a given area. Second, as manufacturers attempt to shrink these solder bumps to increase connection density, the tiny solder joints become highly susceptible to a destructive phenomenon known as electromigration. At microscopic scales, the intense flow of high-density electricity physically pushes the metal atoms of the solder out of place over time, eventually causing the circuit to crack and break, rendering the chip dead. To completely overcome these physical limitations, the System-on-Integrated Chips platform abandons solder entirely, utilizing an incredibly advanced, almost magical technique known as bumpless copper-to-copper hybrid bonding. Hybrid bonding represents the absolute pinnacle of fine-pitch semiconductor packaging, effectively blurring the line between making a chip and packaging a chip. The process is a masterclass in precision engineering. Instead of using protruding bumps of solder, the technology relies on polishing the mating surfaces of the two silicon dies to an almost unimaginable degree of planar perfection. These surfaces consist of a dielectric insulator material, typically a form of silicon oxide or silicon carbon nitride, embedded with thousands of microscopic copper contact pads. To prepare for bonding, these surfaces undergo chemical-mechanical polishing until they achieve absolute planarity, with surface roughness measured in fractions of a single nanometer. The polishing is so precise that it intentionally leaves a minuscule, controlled depression in the copper pads, a phenomenon known as dishing, while researchers utilize sacrificial titanium nitride layers to protect this delicate profile during aggressive processing and prevent thin dies from warping. When these two impeccably flat, perfectly clean surfaces are brought together at room temperature, the dielectric materials undergo a spontaneous hydrophilic fusion. The molecules of the insulators bond together instantly upon contact. Following this initial fusion, the bonded dies are subjected to a highly controlled batch annealing process, a precise, sustained application of heat. Here is where the physics of the materials take over. Because copper metal expands at a significantly greater rate than the surrounding rigid dielectric material when heated, the microscopic copper pads swell, rise out of their dished depressions, press intensely into one another across the bonded interface, and physically fuse together at the atomic level. This creates a permanent, continuous, flawless copper-to-copper electrical connection without a single drop of solder or glue. This incredible atomic-level bonding mechanism allows for vertical interconnect pitches, the distance between the center of one connection to the center of the next, to shrink down to single-digit micrometers. Advanced production and research environments are already demonstrating successful die-to-wafer bonding at pitches of 2 micrometers, and even down to sub-micron scales of 400 nanometers for full wafer-to-wafer integration. In commercial applications, this technology is already being prominently utilized by companies like AMD, which employs the three-dimensional hybrid bonding to stack massive layers of extra cache memory directly onto their high-performance Ryzen and EPYC central processing units, bypassing the traditional micro bumps and achieving staggering power efficiency. To facilitate this integration for other developers, alliance partners are creating ultra-compact input-output cell solutions specifically optimized to fit within these minute hybrid bond bump pitches. However, executing this atomic-level bonding at an industrial mass production scale introduces staggering manufacturing challenges. The most critical, unforgiving hurdle is surface defectivity. Because the hybrid bond relies entirely on direct, flush atomic contact across the entire surface of the chip, even a single microscopic particle of airborne dust or a minute deviation in surface flatness can cause localized delamination. A single particle can act like a tent pole, creating a void around it that prevents thousands of surrounding copper pads from touching, thereby ruining the entire stacked chip. This necessitates pristine, hyper-controlled cleanroom environments that far exceed traditional back-end standards, often requiring Class 3 or ISO 3 atmospheric levels within the robotic handlers, alongside highly sophisticated mini-environments within the manufacturing tools themselves. Furthermore, to drive down particulate levels during the dicing phase, engineers are abandoning mechanical saw blades and lasers in favor of advanced vacuum plasma dicing, which removes material chemically without generating dangerous silica dust or causing microcracks at the edges of the dies. Another immense challenge is managing the delicate thermal budget during the bonding process. Traditional copper-to-copper bonding requires high temperatures, often around 400 degrees Celsius, to force the metal atoms to diffuse and fuse. But subjecting highly advanced logic chips and especially delicate memory cells to extreme heat for prolonged periods can severely degrade their performance, alter their precisely tuned electrical characteristics, or destroy them entirely. To mitigate this, material scientists are heavily researching and deploying the use of nano-twinned copper. By manipulating the microscopic crystalline structure of the copper during the electroplating process to feature a specific preferred grain orientation, the copper atoms are encouraged to diffuse and fuse at significantly lower temperatures. This breakthrough allows for complete, robust atomic annealing at approximately 200 degrees Celsius, protecting the underlying delicate transistors while still achieving a flawless, permanent bond. Engineers are also utilizing low-temperature sputtering techniques to deposit the dielectric layers at temperatures below 250 degrees Celsius. Moisture absorption is another critical enemy. If wafers sit in a queue for too long between surface chemical activation and physical bonding, ambient humidity can corrode the microscopic copper pads and weaken the entire structural interface, requiring incredibly strict time management on the factory floor. Breaking the thermal wall, the frontier of direct-to-silicon liquid cooling. As the System-on-Integrated Chips platform enables the stacking of dozens of high-powered logic chips and massive memory stacks into incredibly dense three-dimensional packages, the industry has precipitated an existential crisis in physics: the thermal wall. In standard consumer electronics, heat is a nuisance. In advanced artificial intelligence packaging, heat is a destructive force that dictates the absolute performance limits of the hardware. As computational power densities surge beyond 4.8 watts per square millimeter, the sheer volume of heat generated by these densely packed vertical structures is simply too extreme for traditional cooling methods to dissipate. Standard air cooling with fans and massive aluminum heat sinks has long been obsolete in this arena. Even conventional lidded liquid cooling systems, which pump water over a cold plate attached to the top of the chip, are rapidly failing to keep pace with thermal design powers that are aggressively pushing towards several kilowatts per package. The fundamental flaw in conventional liquid cooling lies in the thermal interface materials, commonly known as thermal pastes or liquid metal pads, which sit between the hot silicon chip and the liquid cold plate. While these materials are designed to conduct heat, they still introduce a microscopic layer of thermal resistance. When dealing with extreme kilowatt power levels, that tiny amount of resistance acts as a highly effective insulating blanket. It traps heat within the delicate silicon layers, causing localized microscopic hotspots that degrade the integrity of the transistors, increase electrical leakage, and ultimately force the processors into thermal throttling, where they artificially slow down their clock speeds to prevent themselves from literally melting. To permanently shatter this thermal wall, revolutionary research in the field of microfluidics has been seamlessly integrated directly into the advanced packaging platform itself. In a groundbreaking, industry-defining advancement detailed at recent technological symposiums, engineers have developed and demonstrated direct-to-silicon liquid cooling, completely redefining the paradigm of semiconductor thermal management. Rather than placing a separate cold plate on top of a chip using inefficient thermal interface materials, this cutting-edge technology actually embeds microscopic fluid plumbing channels directly into the backside of the silicon structure itself. Through a highly sophisticated low-temperature fusion bonding process, a specialized silicon-integrated microcooler is permanently attached directly to the active heat-generating silicon. This entirely bypasses the intermediate thermal materials, achieving near-zero thermal impedance between the heat source and the cooling liquid. The fusion bonding creates an absolute hermetic seal, ensuring that highly pressurized liquid cannot leak and destroy the immensely expensive electronics, while remaining compatible with ultra-advanced nodes. The design of these microfluidic channels is a marvel of fluid dynamics. Structured as complex microscopic arrays of square pillars, deep trenches, or precisely angled flat planes, the internal geometry is meticulously engineered to optimize the flow of the coolant, typically ultra-pure deionized water. Specifically, the pillar structures are designed to constantly disrupt the smooth flow of the water, intentionally inducing a turbulent flow state. Turbulent flow drastically increases the amount of liquid that comes into direct contact with the hot silicon walls, thereby maximizing the rapid extraction of thermal energy. Rigorous laboratory testing and physical prototype demonstrations on massive 3.3 reticle-sized CoWoS packages have yielded staggering results. The direct-to-silicon microfluidic approach achieved an incredibly low junction-to-ambient thermal resistance of 0.055 degrees Celsius per watt at standard fluid flow rates. This phenomenal efficiency allows these massive artificial intelligence packages to operate continuously at extreme sustained power levels exceeding 2.6 kilowatts while maintaining impressively low internal temperatures that prevent any degradation of the logic circuits. In localized testing, the system effortlessly dissipated heat fluxes exceeding 7 watts per square millimeter on the backside of logic chips, vastly outperforming traditional lidded cooling methods. Furthermore, advanced droplet-based microfluidic electrowetting techniques are being heavily researched to target dynamic, localized hotspots on the fly, offering an unprecedented level of dynamic thermal control. This profound convergence of semiconductor fabrication and advanced fluid dynamics ensures that future generations of highly stacked trillion-transistor three-dimensional chips can operate at their absolute maximum theoretical compute capacities without succumbing to their own immense power generation, with commercialization goals set aggressively for the near future. System-on-Wafer, reimagining the architecture of the hyperscale data center. While technologies like the localized bridge CoWoS push the extreme boundaries of how large an individual rectangular chip package can physically be manufactured, there is an entirely different, highly radical architectural philosophy taking hold for the absolute highest echelons of hyperscale data centers. This approach proposes a simple but audacious solution to the communication bottleneck: abandon the dicing process entirely. This is the foundational concept behind the System-on-Wafer technology platform, a monumental leap that scales semiconductor integration from the size of a large processor to the size of an entire unbroken 12-inch silicon wafer. To understand the magnitude of this shift, one must look at traditional computing architecture. In standard manufacturing, a large circular silicon wafer is populated with hundreds of identical individual processor dies. These dies are then physically cut out, packaged individually, placed onto separate circuit boards, and wired together using copper cables to form a supercomputer. The fundamental, unavoidable limitation of this approach is distance and medium. When data must leave the microscopic, highly efficient environment of a silicon chip and travel across the macroscopic, relatively clumsy copper traces of a printed circuit board or a network cable, it encounters massive electrical resistance. Driving electrical signals across a motherboard requires immense amounts of power to push the signal through the copper, and it introduces massive latency, a delay that severely bottlenecks the speed at which artificial intelligence models can be trained. System-on-Wafer elegantly and completely eliminates this bottleneck by intentionally leaving the individual computing cores continuously interconnected on the original uncut silicon wafer. The data never has to leave the highly efficient, low-resistance silicon environment. The entire 12-inch wafer becomes a single gigantic processor. The sheer physical and computational scale of this technology is staggering to contemplate. A typical system-on-wafer built utilizing advanced 3-nanometer process nodes can span an area exceeding 70,000 square millimeters, effectively integrating approximately 10 trillion transistors onto a single continuous sheet of silicon. This provides a vast computational landscape where millions of highly optimized computing cores and tens of gigabytes of extremely fast, localized static random access memory are permanently fused together through a massive, unbroken two-dimensional network-on-chip mesh. The critical metrics that dictate artificial intelligence inference and training performance, specifically localized memory bandwidth and the speed of inter-core communication, see exponential, paradigm-shifting improvements under this wafer-scale architecture. In a wafer-scale environment, the die-to-die communication efficiency operates at microscopic fractions of a picojoule per bit. This makes data transfer across the internal wafer network hundreds of times more energy efficient than traditional board-level networking between separate chips. Furthermore, the aggregate memory bandwidth across the wafer reaches tens of petabytes per second, eclipsing the capabilities of standard multi-chip packages by orders of magnitude. This radical architectural concept is not merely theoretical, it has already been triumphantly validated in the commercial market, most notably through the creation of the Cerebrus wafer-scale engine processors, manufactured in deep, exclusive partnership with the primary foundry. The third-generation iteration of this massive chip, the WSE3, serves as an absolute masterclass in wafer-scale engineering. Manufactured utilizing a highly optimized 5-nanometer process technology, the WSE3 boasts a mind-boggling 4 trillion transistors and integrates 900,000 artificial intelligence-optimized cores onto a single silicon square. It features 44 gigabytes of ultra-fast on-chip memory and an astonishing 21 petabytes of memory bandwidth. By completely redesigning the underlying matrix math engines to utilize incredibly wide floating-point simulation units, the WSE3 delivers over double the computational performance of its predecessor, creating a single chip that operates as a complete, self-contained supercomputer. When clustered together into hyperscale formations, these systems can be loaded with over 1,000 terabytes of specialized parameter memory, creating exaflop-class supercomputers capable of handling language models with up to 24 trillion parameters, effectively dwarfing the capabilities of traditional clustered architectures. However, successfully building an entire interconnected system across a single wafer introduces highly unique, monumental software and hardware engineering challenges. The most obvious issue is manufacturing yield. Because manufacturing a perfectly flawless 12-inch silicon wafer without a single microscopic speck of dust or atomic defect is practically impossible, the system must be inherently, structurally fault-tolerant. If a single transistor fails on a normal chip, the chip is thrown away. To solve this on a wafer scale, the architecture employs brilliant hardware-level remapping. The system automatically maps and recognizes physical defects on the wafer during testing. Then, it utilizes highly redundant silicon communication links and low-level software drivers to silently bypass the dead cores, routing data around the microscopic damage and presenting a virtually perfect, unbroken computational mesh to the software developer. Furthermore, the programming model for a wafer-scale system must be entirely restructured from the ground up. Because data takes significantly longer to travel from one side of a 12-inch wafer to the other compared to traveling across a tiny conventional chip, developers must navigate highly non-uniform memory access latencies. The software must utilize distributed asynchronous message passing and specialized routing protocols to ensure the data is placed exactly where it is needed and prevents massive data traffic jams across millions of cores distributed across the vast silicon landscape. When properly optimized, specialized software frameworks running on wafer-scale systems have demonstrated the ability to reduce per-user large language model inference latency to less than 1 single millisecond, an astonishing feat of speed that is currently physically impossible for conventional hardware limited by off-chip memory bounds. Looking toward the near future, the foundry's System-on-Wafer roadmap is rapidly evolving into the highly anticipated next-generation CoWoS platform. Scheduled to enter commercial volume production by 2027, CoWoS will drastically expand the capabilities of wafer-scale computing by moving beyond the foundational boundaries of the original iterations. This next-generation platform is designed to seamlessly integrate massive compute dies, external memory, and cutting-edge optical network interconnects directly into the wafer structure itself, delivering computational power estimated to be 40 times greater than current standard advanced packaging solutions. It is a technology specifically tailored to process the massive multi-trillion parameter language models that will inevitably define the next decade of generative artificial intelligence, delivering thousands of watts of localized power to a single integrated system. Silicon Photonics and COUPE, letting there be light in the data center. Even as the compute density inside these advanced CoWoS packages and massive wafer-scale systems reaches stratospheric, unimaginable levels, the semiconductor industry faces yet another harsh, unavoidable physical barrier: the input-output bandwidth and energy wall. Processing trillions of calculations per second is only useful if that data can be rapidly ingested from the network and immediately exported back out to other servers. Historically and currently, all data center networking relies heavily on high-speed copper electrical cables and traces routed across circuit boards. However, pushing massive amounts of electrical current through tiny, highly resistive copper wires over long distances at incredibly high frequencies creates severe signal degradation and generates enormous amounts of waste heat. In modern, state-of-the-art hyperscale data centers, an increasingly alarming and unsustainable percentage of the total facility energy budget is spent simply moving data from one server rack to another over copper, rather than actually computing that data. The electrical resistance of copper forces network engineers to use highly power-hungry signal amplifiers to ensure the data reaches its destination intact. Electrons, the fundamental carriers of electrical current, have simply reached their absolute physical limits as a viable medium for long-distance, high-bandwidth data communication. The ultimate, scientifically sound solution to this impending energy crisis is a complete transition from the realm of electronics to the realm of optics. Silicon photonics is the highly advanced technology of using rapid pulses of laser light to transmit digital data through microscopic optical glass fibers. Light, consisting of photons, does not suffer from the same electrical resistance, signal loss, and heat generation as electrons moving through copper. This allows for vastly higher data bandwidths to be transmitted over significantly longer physical distances, while consuming only a minute fraction of the energy required by traditional electrical networking. To integrate this massive optical revolution directly into the highly standardized mass-production silicon manufacturing pipeline, the foundry developed the Compact Universal Photonic Engine, widely known as COUPE. The COUPE architecture is a masterpiece of heterogeneous integration, designed specifically to seamlessly, flawlessly meld the traditional electronic world with the new optical world. The system fundamentally consists of two highly distinct specialized parts. The first is the photonic integrated circuit, which is manufactured on a silicon wafer and contains incredibly microscopic optical components such as micro-ring modulators and highly sensitive germanium photodetectors. The micro-ring modulators, manufactured utilizing advanced 3-nanometer process nodes, are tiny resonant silicon rings that interact with a continuous laser beam, turning the light on and off billions of times a second to encode digital data onto the optical signal. The second part is the electronic integrated circuit, which serves as the traditional digital brain, containing the logic required to control the lasers, drive the modulators, and interface smoothly with the server's main processor. In traditional, older silicon photonics setups, these two distinct components are placed side by side on a common substrate. However, placing them side by side still requires a short, high-speed copper electrical trace to connect them together, which immediately reintroduces the exact electrical latency and power loss the system is trying to avoid. The revolutionary COUPE platform completely solves this inherent flaw by heavily leveraging the advanced system-on-integrated chips vertical stacking technology. By directly vertically stacking the digital electronic integrated circuit perfectly on top of the photonic integrated circuit, using the incredibly precise bumpless copper-to-copper hybrid bonding previously discussed, the electrical path between the two domains is shortened to the absolute physical minimum, mere micrometers. Through-silicon vias are utilized to route power and high-speed data signals vertically straight through the stack, completely eliminating the severe parasitic impedance and signal loss associated with traditional flat lateral wiring. This unique vertical configuration drastically improves the overall energy efficiency of the system and significantly lowers the transmission latency. Two absolutely critical, non-negotiable requirements for optical interconnects powering high-speed artificial intelligence neural networks. Furthermore, the physical structure of the COUPE engine is engineered as a solid monolithic-like entity. Unlike older photonic platforms that relied on fragile, mechanically weak cavities or hollow structures to route light, COUPE's solid-state design prevents contamination and mechanical failure. This incredibly robust design results in exceptionally low optical insertion loss, meaning very little light is wasted or scattered, whether the system is using grating couplers to connect fibers to the top surface of the chip or edge couplers to connect fibers to the side of the chip. The strategic, highly aggressive rollout of the COUPE platform is carefully staged to completely overhaul global artificial intelligence networking over the next few years. The technology is slated for initial qualification and integration as small form factor pluggable optic modules by the year 2025. This initial phase will provide an immediate, highly necessary performance and energy upgrade to existing traditional data center network switch architectures. However, the true industry-shaking paradigm shift is scheduled to occur in 2026, when the COUPE engine is fully, seamlessly integrated directly into the massive CoWoS packaging ecosystem as co-packaged optics. By embedding the optical networking engine directly onto the exact same organic or silicon interposer as the main logic processors and high-bandwidth memory, co-packaged optics effectively brings the massive bandwidth of a fiber optic cable straight into the very heart of the processor itself. This monumental achievement entirely eliminates the need to drive high-power, heat-generating electrical signals across the server motherboard to reach networking switches located at the edge of the server rack. The end result is a revolutionary optical interconnect platform capable of delivering multiple terabits of data bandwidth at completely unprecedented energy efficiency levels. Future iterations of the platform are already targeting mind-boggling bandwidths of 6.4 and 12.8 terabits per second, effectively tearing down the input-output bottleneck that currently starves modern multi-million-dollar artificial intelligence accelerators of the data they desperately need to function. The ultimate synthesis: compute, memory, and optics united. The profound, sweeping technological achievements unfolding daily within the back-end manufacturing space signify much more than just a faster computer. They represent a fundamental, permanent reimagining of how all high-performance computing systems are designed, architected, and physically built. We are witnessing the death of the monolithic processor and the birth of the highly integrated three-dimensional system. This new era is defined by extreme, unprecedented collaboration across the entire global technology sector. A prime example is the ongoing development of next-generation high-bandwidth memory, particularly the upcoming HBM4 architecture. Moving forward, the critical base die of these massive memory stacks, the intelligent controller that manages the flow of data at the bottom of the memory cube, will no longer be manufactured using older, slower memory processes by traditional memory makers. Instead, leading memory manufacturers like SK Hynix have entered into deep strategic partnerships with the primary foundry to manufacture these base dies using cutting-edge, ultra-fast logic nodes, such as advanced 12-nanometer and 5-nanometer technologies. This trilateral collaboration between product designers, memory manufacturers, and logic foundries ensures that the memory can seamlessly integrate with the logic processors within the CoWoS package, introducing integrated voltage regulators directly into the package and breaking down the final performance barriers for artificial intelligence applications. As the rigid, historical boundaries between traditional memory production, front-end foundry manufacturing and back-end advanced assembly completely blur into a single cohesive process, the 3D fabric ecosystem stands as the undisputed central hub of this massive global effort. By mastering extreme lateral expansion through massive reticle-busting CoWoS interposers capable of supporting dozens of memory stacks, pioneering unparalleled vertical density with bumpless, atomic-level hybrid bonding scaling down to sub-micron pitches, redefining the very concept of scale with entire system-on-wafer architectures bypassing printed circuit boards, and permanently breaking the energy and bandwidth barriers with deeply integrated solid-state silicon photonics, the semiconductor industry has successfully forged a brilliant, sustainable path far beyond the physical limitations of traditional silicon scaling. The microscopic, once-ignored back-end architecture has unequivocally become the macro-level enabler of human technological progress. As global society stands on the precipice of advanced generative artificial intelligence, ubiquitous autonomous systems, and hyperscale supercomputing, it is these invisible, meticulously engineered three-dimensional fabrics of silicon, copper, liquid coolant, and light that will ultimately power the future of digital innovation.